For application of echoes, sorry, I said waves just now, I meant echoes. Some information is given in your textbook. There are 2 or 3 points that you need to know. So you go to page number 151. Incidentally, I managed to get a copy, 2021 copy of the textbook. So now we will all be on the same page. So I hope you people have the textbook and you are turning to the referred page. I'm just going to kind of go through the points over here and discuss anything that is relevant. Okay. So under the section 7.5 uses of echoes, echoes find their application in sound ranging and echo depth sounding by using ultrasonic waves. I'll just put the textbook over here. So I'm reading from this section. Some introductory material is written over there. You can mark these sections as just for general reading. There are 3 points which can kind of, so the points are they can travel undeviated through a long distance. They can be confined to a narrow beam and they are not easily absorbed in a medium. Any of those points require any elaboration? I think, what do you people think about point number 3? Anybody would like to hazard a guess why that point is mentioned over there? It says that high frequency sound waves, what we call ultrasonic waves, they can be used for a variety of purposes. They have a high amount of energy than audible sounds. 20,000 kilohertz and above we can't hear. But their advantages are they can travel undeviated through a long distance. They can be confined to a narrow beam and they are not easily absorbed in a medium. The first 2 points I can kind of understand. The third point, is it clear? They are not easily absorbed in a medium. Why does that become an advantage?
They actually reflect back without getting absorbed.
No, even sound waves, when you have a hard surface, even sound waves will get reflected without being absorbed. Absorption as far as audible sound waves are concerned has got to do a lot with the material of the medium. The surfaces, the contours and so on. The hardness of the surface, the smoothness of the surface. But here they are talking about medium. That's why I want you to pay attention to that.
Isn't the third point kind of similar to the first? I mean,
yes.
Not absorbed.
Correct. They are able to travel undeviated. I mean, undeviated is a different thing, in the sense that they do not get. I don't know why they say undeviated. Actually, even the first point is something to think about. They are saying undeviated. If you say they can travel for a long distance, that has got something to do with the third point. I agree, they seem to be connected. So in what way are they connected? Well, it's straightforward. If the medium itself starts absorbing the sound energy, then it's not going to travel a great distance. Okay, so that might be one factor. The undeviated part is probably coming because normally sound waves can get easily deviated. In fact, thermal variations can also cause a deviation in the sound wave. So if you have the material medium, let's say air, and the air is warmer near the ground and cooler above, or the other way around, right? We have explored this last year. Then the sound waves do bend. They refract just like light waves refract. So sound can also refract. But I think the ultrasonic sound waves they have this property that they do not get easily deviated. They will get deviated, but I think the amount of deviation that occurs is not as much as for audible sound. If somebody has any explanation for why that is so, we can talk a little bit about it. Otherwise, I don't want to confuse everybody with that consideration. We can move on. But do think about it. It will be interesting if we can get some insight into that. Why is it that high frequency sound waves, the ultrasonic waves, why they do not deviate so much? And also that the amount of energy in the ultrasonic wave is such that they do not get absorbed by the medium. Okay, so the medium does not kind of dampen the energy in the wave. So that is the reason why it can travel far. I'll move on then after that. There's
So, so isn't it like friction force? Once you break the friction coefficient, it goes on for like it goes on easily, and I mean, as
but
in since the energy is lesser for the
yeah, but the friction coefficient will be between the particles of the medium themselves, right? So why would the particles friction coefficients change?
no, as in I'm saying that I'm taking an analogy. So it's basically like the high energy particles don't lose as much energy because they they basically don't travel for the same amount of time in the no they do.
Uh,
Sorry.
yeah, there might be something in what you're saying. Basically, there might be a maximum amount of absorption of the energy that is possible for a medium, right? So therefore, if you have a high energy wave passing through, a small amount of the energy will get absorbed by the medium, but most of the energy probably passes on beyond that point. So therefore, it contains a lot more energy, and therefore it travels further. We are just thinking about it from first principles. We may be completely wrong over here, but I wanted to have a discussion on this so that it kind of registers in our mind. What are the factors due to which we use ultrasonic frequencies for these purposes? You can't use any old sound wave for the purposes of what we are going to discuss further. Okay, so I want you to remember this point that there's something special about ultrasound. It does not get absorbed by the medium. It can travel undeviated for a long distance through a medium, and they can be confined to a narrow beam. That's because you produce them yourself. So you can sort of propagate it through a dish or something like that. When I say dish, I mean like a dish antenna dish. So you can kind of send it out in one particular direction. Whereas generally, if you produce sounds, they go out in all directions. So if you remember these 3 points, it's a possible question. I've never seen this question being asked in the board before, from my memory, from the top of my head. But they could ask a question like, name one property of ultrasonic sound that makes it useful for sonar, let's say, or makes it useful for echolocation in some animals. So you can mention one of these points or two of these points as the case may be. So we'll carry on now. We'll move on to the actual applications themselves, which is that echolocation used by bats, dolphins, and as if fishermen also fall into the same category. They have mentioned fishermen also. Well, bats and dolphins, yes, as organisms, they seem to have this capacity to produce near ultrasonic sound waves. I'm saying near ultrasonic because I have often noticed in videos that are made of these animals that you can actually hear the clicks, particularly for dolphins. I'm not so sure about bats, but bats also make some screeching sounds. I'm not sure that is the sound they use for echolocation, but that might well be. But I think that they are near ultrasonic, not ultrasonic, or they may be having a frequency range that goes from near ultrasonic to ultrasonic. And the remarkable thing is that they are able to navigate through their ecosystems. Bats are nocturnal, so they move about at night. Dolphins also dive deep, something like if you go below 15 or 20 meters underwater, hardly any of the surface light gets through. So even during the day, if you dive beyond 20 meters underwater, it's going to get dark. So dolphins and bats seem to use this method of echolocation to find out where their prey is, and it kind of works something like this. So the whole thing is that they use echoes. So I'll attempt to draw a bat as best as I can. Okay, so say that's a bat flying about, okay, and it's looking for a prey, something to eat. And here, the ground below it is one of these giant bandicoots that I hate. It's really scary looking at them. And what the bat does is it sends out an ultrasonic frequency waves in all directions. I suppose it suspects that there is something to eat over there, and it sends out these high frequency waves. Now, what happens is that if there is a plain flat surface, what you expect from a blank, yes,
Out of the board.
Do you mind moving the board slightly to your left?
fine, that's the edge of it actually.
Oh, okay.
Okay, so then what will happen is, let's say the sound hits a wall or something, maybe a tree over there, okay? Then the sound is going to get reflected back to the animal in a particular way, which tells it that there is a hard flat surface like a tree. One moment, Vaishnavi is here, I'll just admit her. I suppose just like languages and just like learning how to distinguish between objects, bats also go through the same process as they grow up. They pick up the cognitive ability to make out the difference between a surface which is something to be avoided and a kind of surface which might mean a potential prey. So sound waves that are then reflecting, let's say, off the ground over here, that's also reaching back to the to the bat in a particular manner. Now, what happens over here is that the sound waves that are reaching the animal, right, they are going to be deflected in different directions because of the contour of the animals. Okay, so there is going to be a break in the amount of energy, I suppose. I'm going to just take it as energy, which is supposed to be reflected back to the bat, right? But what is happening is there is a break in this signal. Okay, why? Because some of the energy has got dissipated in these directions, right? Now that's going to tell the bat that there is something that can be investigated in that direction. So obviously it's going to go closer, emit more high frequency sounds or emit sounds that are focused more on that region. And by doing this continuously and flying closer and closer to the animal, the bat may be able to locate its prey. Now what it does after that is up to it, but basically I think that is the idea. Now, this is very strange to us because we don't use our hearing as a primary sense, right? We use our hearing in a secondary sense. For us, the primary what can we call it? The primary sense. Yes, the primary sense is vision. Okay, when there is sufficient light, we use our vision to navigate the world around us, and we use sound as a peripheral sense. But in the case of the bats, at night, it may well be that their echolocation is the primary sense. So we need not be surprised, because that is the way it has evolved, that it uses echolocation as the primary sense to find out things. So for the bat, seeing is unavailable, so therefore it uses its hearing, and hearing may be just as good as our sight for the bat itself. If that is understood, then there is no problem understanding how these animals use echolocation. For them, it's just like seeing. Most probably, I can't say for sure. I don't know anything about bats. Uh, but if you think that that is the way they actually see the world, then there is no problem understanding that that's how it works for them. Dolphins apparently do the same. They do it underwater. They could be more efficient than bats, and this is what I am being told. And we use the same principle for deep sea trawling. That is, when fishermen go out into the ocean, what they do is that they use this fact that high frequency ultrasounds can be emitted by a device and then received back, and the image of whatever ultrasounds are coming from below can then be interpreted by the computer and information given as to what is there below it. So if you have a boat or a ship that's supposed to be sails, sorry, I don't know why you use a sailboat for fishing, but anyway, I like sailboats, so I'm just going with sailboats. And let's say that you emit ultrasound frequencies below, and somewhere deep down below there is a shoal of fish, big fish, tuna, marlin, yellowfin, whatever. Okay, so there are thousands of fish that are there over here. So what's going to happen is that the strength of these ultrasound waves, which are going to be reflected off the floor, right? They are going to be different if the fish is there and the fish is not there, right? So if the fish is there, then you're going to have some of the incoming low bound waves that are going to be reflected in different directions, right? And obviously if that happens, then the strength of the wave that is reaching the boat again is going to change. Now that can be used for imaging, right? The strength of the signal that is received back can be used for imaging, and it can be interpreted and shown on a screen, right? And then the fishermen know that there is something that needs to be trawled down there. If they have a very good computer and a very good ultrasound emitter and receiver, then they might even be able to guess the size of the fish, the size of the shoal, and make a decision about whether they need to cast their nets or not. These are huge nets. They are called purse seine nets. The nets are deployed like this, okay, and they have an opening, so the nets will be over here. And then what they do is, in fact, sometimes there are more than one ship. There are two ships that pull these nets. So they can set this net at the appropriate depth and then pull it through. Then everything that is there in the path of the opening of this net will go into those nets. So these are trawling nets. And then they are hauled in by the ship after it has passed the point where the fish are. So this is one such application. Okay.
Arun sir,
Questions about it?
Arun sir,
Yes.
you asked us to remind you when it's 12:50.
So thank you for the reminder. I'll wind up now. So a similar thing can also be used. In fact, it's exactly the same thing. Naval ships, submarines also have to use the same principle to find out if there are, to first of all navigate them under the water if it's a submarine, and if it is ships like destroyers and so on that are going on sailing on the surface, then they can use this application to find out if there are objects beneath, the size of those objects, and therefore what they could be. Maybe it's an enemy submarine and they want to torpedo it, so it's also used for war purposes. This particular application is given a name. It's called SONAR. You can look it up in the textbook what SONAR is. And that's again one routinely asked question. They ask what is a sonar, how is it used in the Navy or in submarines. You just, if you read the section that is written over there, you will get a good idea of what to write. One last thing is ultrasound or ultrasonography, as it's called, is also used for diagnostics purposes. Any of you who'd had siblings recently, you might have seen, even in movies they show these sometimes, you might have seen these pictures of your sibling in your mother's womb or belly, or your relative's womb or belly, and you can see the shape of the child. Now it's not just for done just for sort of amusement of the family members. Ultrasonography has a purpose. Ultrasonography is done to keep track of the growth of the fetus. Okay, so there are specific periods of time when the obstetrician will, that is the doctor who handles pregnancy and delivery, the obstetrician asks the mother to go and get an ultrasound done. And these ultrasound indicate normal healthy development of the fetus, so you can find the fingers. So the ultrasonography doctor, the sonography doctor also interprets these images. They tell you, okay, here we can see the fingers, you can see that the heart is developing, the heart is beating, because you can also make a video of the ultrasonograph. Then you can also see some movements. And if you are very lucky, when the ultrasonography is being done and the child kicks or turns, then you can also see the kick and the turn. It happens very rarely. It's very exciting to see. There is a downside to this. In a culture like in India, what happens is that the ultrasonography can also be used to determine the sex of the fetus. So they can find out if it's a male child or a female child very easily by looking at the development of the sex organs, of the fetus. So what happens is that if in some parts of our country, it's pretty widespread, they find out that if it's a girl child, then there is a possibility that the parents, if they are of such a background, uneducated or not clear about what is it that they are having a child for, then it does happen that they abort the child. If the child, if the fetus is not developing properly, so it's, let's say that its internal organ development is not proper, then it is possible also to legally abort the child, because the parent then has the choice to decide whether they are able to handle a child which is born with some deformities. Then it is possible to legally abort the child. It is not possible, that is ultrasonography has been banned for sex determination purposes in India. So people who, clinics who do ultrasonography to determine the sex of the fetus are punishable under Indian laws. So that's just one another aspect to this whole thing. And ultrasonography, of course, can be used not just for determining the healthy development of the fetus. It can also be used to look at our internal organs, like for example, the lungs, the heart. It's possible to look at all of these organs using ultrasonography. So with that, we kind of come to the, wrap up this section of things. In the next class, when we meet, we will take up natural, damped and forced vibrations. Do come prepared. That's all for this class. If there are any doubts or questions that you have that you want to ask, you can ask now. We have another 3 minutes left.